in this exercises simple directory. And after that, Pedro will take over and show you how to run various applications on Kebnekaise. So there will be examples here for serial jobs, MPI jobs, GPU jobs, also OpenMP jobs. And you get to try out some different constraints also, how to get specific CPUs or GPUs. For consistency, in all the examples batch script, I have given them the suffix .sh, even though it's not required. Again, you can use that or .batch or .sbatch or none at all or some other one. Just do something that makes it easy for you to find your submit scripts in the directory. Any programs mentioned in the batch script, you need to compile them first before you can run it. And that is except for the compile run.sh and the CUDA example, which both includes compilation. Again, repeat of the project ID and directory. And now when you do these examples, if you can try, just run them, and you can also try and make changes to them in any way that you feel like. For the test examples, inside the batch script, I have used FOSS 2022b, and that goes for almost all of them except for the GPU example. If you change it, then you need to change it in the batch script as well. So use the same one that you in the batch script as you compiled it. In most examples in the batch script, I name the executable as the program itself, but without the .c or something. And you can do that, or if you don't, or if you name it something else, again, change it in the batch script. And I'm just going to remove all my Slurm files, so it's easier to see what we have here. And I have these files here that are in the exercises simple, and there are also some that I have now compiled, as you saw earlier. But in each of the cases here for the exercises, there is an explanation first where you compile, how do you compile it, and then how does the batch script look like. You can also look at, for instance, the one hello.sh with nano. And when you do that, you could also make changes to it if you want to. So if you used a different compiler toolchain, you would change it here. Remember, hold control down, push X to exit, and save it if you have edited it. And in each case, you have some exercises you can try around with there. There's an MPI one. It's the one we test run earlier. That's the OpenMP run one. And there is also an example where you run multiple serial jobs from the same submit file. And in order to use it, you need to first compile those 4 here. And here is how it looks inside. There is not much to say here aside from 2 things. First, you need, if you're running multiple serial jobs, then you need to ask for enough cores that all jobs can run at the same time. And then you add an ampersand at the end of each line, and except for the last one, and then you put wait. If you don't put wait, then it will end the job as soon as the first of these jobs inside and stops running. But if you put wait, it will wait until all of them has finished running. And then how to run it. There's an example of job arrays, and job arrays is another way of submitting and managing collections of similar jobs. They need the same initial options, size, time limit, etc. You can though change some of them after the job has begun execution, but it's easier to just have some that use the same. And this is an example of a Python job that it's very simple, and it's just one that I made in order to test this job array here. And here you need to use the Slurm directive, which is -- array, and then how many tasks you want in the array. And then how many cores you want per task. And then you would submit it with srun, and because it's a Python script, Python, and then the name of this script, and then the number it is in this array. Again, try it also. There are multiple parallel jobs sequentially. If they are after each other, then you only need enough cores to run the largest of them, because they run one at a time. If they run at the same time, then you need enough cores for all of them to run at the same time. Also, you need enough time for all to complete. As an example of compiling inside of the job before running it. There's an example of splitting in separate files the errors and outputs. And then we come to some CUDA or GPU programs. There's an example for V100. And in this case, it also does the compilation inside of it. And there's also one for for an A100. And here I'm just loading CUDA, and then quick explanations of how you would do it for various features, so you can play around with that. Then finally at the end, there's if you have more time over, but this is something I believe maybe Pedro will also talk about. You can start Jupyter on HPC2N. It's possible to run it, and this has to be done from inside of HPC2N. So that means you will have to use ThinLink if you do that. And on this page here, there's documentation on how to run it. So basically, you are making a batch job that is asking for resources on a node where it then starts the Jupyter server, and then you connect to that. But it's explained here. Okay, so there are a number of exercises here for some simple batch scripts. They are all in the exercises simple directory. Under this directory you cloned with git clone. And the idea now is to spend some time looking at them, and let's take until 1350 maybe, and try it out.